Kabunka, good afternoon everybody. My name is Mark Shields. I'm the Vice President of Hydrogen Energy Systems. First of all, I'd like to thank everybody for finding the time to attend this excellent event, and my continuous thanks goes to GTCC AKN in Thailand for organising these roadshows hosted in Puket and Krabi, and indeed their work in promoting hydrogen-based renewable energy systems as a route to carbon emission reduction in Thailand. Unfortunately, I am unable to attend this event, and indeed I have to provide this presentation virtually before boarding a flight. My colleague Kun Thorsen, however, who is also present, will be very delighted and very capable to answer any questions you may have after his introduction. H2 Core Systems is a German-based company specializing in the design, assembly, implementation and servicing of fully integrated hydrogen energy storage solutions. We believe in hydrogen as the most important energy carrier of the future, and we have made it our mission to become the most respected and innovative company providing clean, uninterruptible energy solutions to remote locations in Southeast Asia. Of particular significance to myself is my own personal involvement in the Pui Shi House project in Thailand, in Chiang Mai. This is the world's first solar hydrogen multi-house community which has been operating off-grid since January 2016. This project demonstrates to the world how sustainable living can be achieved in Thailand, where in effect this technology was first developed and tested. The topic I was asked to speak about was how to transform potential into projects. So let's first take a look at some of the features of hydrogen. Hydrogen is the first chemical element of the periodic table. It's the most abundant element in the universe. We are surrounded by it. It is the lightest and simplest element we know, consisting of one proton, one electron, yet it is high in energy. Hydrogen is not an energy source per se, but an energy carrier, and it has great multiple talents. It can be transformed into electricity, used as fuel for transport, used for heating and cooling purposes, as well as other industrial applications. But free hydrogen does not occur naturally in quantities of use like other energy sources, but can be generated by various methods. As such, the feasibility of a hydrogen economy depends on issues including the generation of sustainable energy and actual energy sourcing. Green hydrogen, when generated through renewables, is a multi-talented when it comes to replacing fossil fuels. With solar or wind or indeed any renewable power and with water, we can provide easily storable, transportable, versatile energy for all applications. This wonderful molecule gives us the tool to decarbonize all sectors in Thailand, including those who have proven difficult to electrify. The wealth of Thailand comes from its diverse environment and warm climate. This provides a golden opportunity to electrify remote areas with local energy, in this case the sun. It is renewable and can endlessly supply hydrogen. All we require is sun and water. The cost of hydrogen therefore depends on the cost of electricity, of which PV at the moment provides the lowest cost of entry, now being measured in cents for watts. So our building block, if you like, is based around the Adapter AEM electrolyzer. This is a microwave size device that can produce 500 litres per hour at 35 bar pressure, similar to the pressure in your car tyre. This pressure, however, provides a meaningful amount of hydrogen to store in a relatively small space without needing to include complex compression devices. And as such, it allows for virtually unlimited amount of energy to be stored indefinitely. This electrolyzer, the Adapter electrolyzer, produces 500 litres per hour. In 24 hours, I can produce 12 cubic meters, which is approximately 1 kilogram. And if I consider that stored in a 1 meter vessel at 35 bar, that will provide me with approximately 50 kilowatt hours of electrical energy. So firstly, My microwave-sized device can produce 500 liters of hydrogen per hour, but what does that actually mean in reality? Well, 500 liters weighs about 40 grams. It has the energy of about 2 kilowatt hours, or what we call the LVH energy. That in itself will be enough to drive a car for 10 kilometers, or enough through a fuel cell to provide power for a high-end computer desktop and lighting in a sort of room environment. That same device, if I operate it for a full day, would be enough to drive that car for 100 kilometers. If I have 5 of them and I'm operating in a day, I could drive that car for 500 kilometers. So one of the advantages of building our solutions around the adapter electrolyzer is pretty much scale. So if you are old enough to remember mainframe computers, you basically bought a very large computer to do a particular job and you were stuck with that size forever. Mainframe computers have been effectively replaced by networking PCs together, and in the same concept we are basically networking these individual modules together to produce the volume and the scale of hydrogen that is required for specific projects. And by doing that, we get the advantage of mass production, the same net effect that we're seeing in the solar industry, where the price of solar panels reduced over time due to scale. We see the same effect happening with the AEM electrolyzer type solution to the hydrogen market. From our perspective, we can literally provide a solution from several kilowatts up to a megawatt in capacity. So to make any use of hydrogen in terms of converting that hydrogen into electricity, for example, we do need the help of the fuel cell. So I want to explain a little bit about how a fuel cell works, and in particular to focus on its advantages over using, say, traditional technologies like batteries or diesel generators. So a fuel cell basically consists of 2 electrodes, a negative electrode or anode and a positive or cathode, sandwiched around an electrolyte. Fuel, such as hydrogen, is fed into the anode and air is fed into the cathode. The most common name of fuel cell that you'll probably hear of is called a PEM, proton exchange membrane, and this is where a platinum catalyst is coated on the anode, and its job is to separate the hydrogen atoms into hydrogen ions or protons and negatively charged electrons. The negatively charged electrons basically have to go around the outside or the circuit itself to catch up with the hydrogen proton, and this is what provides electrical energy. Now, a single plate in itself can only potentially provide 1 volt of power, barely enough for the smallest applications. So to increase the amount of electricity that's needed or generated, we put these sandwiches into what we call a stack, and stacks are typically available from several hundred watts up to pretty much megawatt capacity now. There are many types of fuel cells out there, but PEM is probably the most common for applications such as ours, in that they operate at relatively low temperatures and they can quickly meet the power requirements to suit the load in a very sort of fast and responsive way. Fuel cells are a source of clean, stable power. They produce no emissions. The exhaust that is produced is actually water, where oxygen from the air is met with the hydrogen, who gets its electron back. So there is no bad emissions coming out of fuel cells at all. And I guess the biggest sort of single factor when you compare them as power generators to, say, diesel generators, is the reaction itself is a chemical reaction, so there's no vibration, no moving parts, and no noise. And more importantly, for sustainability and lifetime, there's no consumables like oil or oil filters or belts or lubricants. So what we basically do is we combine electrolyzers and storage and relative items to convert it into electricity or to allow people to use hydrogen for other means. And we build these modules based on either an outdoor or indoor cabinet design, or even 20-foot containerized design, or 40-foot containerized design. And the type of applications that we've provided enable people to use that hydrogen to produce power through a fuel cell, use that hydrogen to produce synthetic fuels such as e-ethanol, e-methanol, and some of our clients in fact use hydrogen as part of their manufacturing process. For example, companies that make ammonia or fertilizer, hydrogen or glass. Hydrogen is one of the main ingredients, and being able to produce this on site in your factory rather than ordering hydrogen from a gas supplier, which will probably deliver you grey hydrogen, is allows some of these manufacturers to be able to claim quite a lot of green elements in their product itself. So we basically provide solutions to enable the hydrogen economy, and the sort of solutions we provide fall into a variety of sectors. And I think the most common sector, I guess, would be providing power for remote or off-grid or bad grid type environments. The Route de Mafe, which is the picture on the top left here, is a good example of this. It's in a mountain range of Reunion, which is a remote island in the Indian Ocean, and it's classified as a UNESCO Heritage World Site. It's also home to 700 inhabitants. It has no roads, it's accessible only by foot, and the microgrid on the island provides electricity through 100% renewable resources. The system is completely fossil-free, comprises PV, hydrogen production, hydrogen storage. The power produced by solar panels is used first to satisfy the load or the demand, and when that is met, the solar panels charge a small battery bank, which is used for bridging energy, and the rest is used to produce hydrogen. And based on the storage they have basically autonomy or backup for 5 days, up to actually 15 days autonomy in the event of storms and typhoons that frequently come across the island. The location itself would be fairly typical in terms of the type of applications that we're providing power for. We have a community of houses, we have a medical dispensary, a workshop, and this system is operating for quite a while and has demonstrated that it can basically fulfill the requirements that cannot currently be met by batteries or with the liability you have with a diesel generator when you don't have access to fuel. Other applications that are starting to become more popular now is using hydrogen as a way to get rid of electricity that you can't currently use on a much larger scale. So, for example, one of our clients, they run a data center. They use green electricity for the data center, but basically if they don't consume that electricity, they lose it. So what they basically do is they dump unused or available electricity onto a bunch of our electrolyzers, and our electrolyzers can very quickly respond from being given power to go into full production. So we pretty much can harvest and utilize that energy load. This is, I think, going to become this sort of energy storage and reuse later for anything from utility companies to large power users. I think is going to become quite popular in the long term. In addition, we also provide hydrogen for vehicle type applications. Now, it's going to be a while before we're refilling lots and lots of cars. We do refill cars in Germany and a few other countries at the moment, but we see particular applications in Asia for refueling for things like forklifts. So one of our projects we're doing in Singapore at the moment is for a logistics company. They have 10 forklift trucks, I think, and we put solar panels on the roof. We produce hydrogen in their car park instead of the forklifts being charged using the grid, which according to the government in Singapore contributes 65 metric tons per forklift charge. That problem goes away. We substitute the batteries in the forklift with fuel cells, and this sort of light transport applications, whether it's forklifts or resorts that have small buggy type vehicles, I think is really going to start to be adopted very quickly in Asia as well. And then finally, as I mentioned before, some of our customers use this to produce synthetic fuels. They produce e-ammonia, e-methanol, e-ethanol, and finally, we're starting to see some interest from feedstock producers in Asia who require hydrogen, and it's expensive for them to buy because they have to buy it from a gas provider who is many, many, many miles away, and most of the cost of their hydrogen is in actually the transporting of that hydrogen to their site. So if they can produce hydrogen on site where it's actually needed, they have significant savings as well. So I guess in terms of the topic I was asked to address, which is how to transform potential into projects, I guess the simple answer to the equation is we have to apply what I call the Benjamin Franklin factor. Now, this doesn't mean that green is the color of money per se, but basically it has to make sense for the user, and it has to make sense for the person who has to use the equipment and the benefactor of the result of using this equipment. So we normally see a number of projects starting to appear. So in terms of a potential project, I think they fall into several categories. We have like what I would call the feel-good project, where a corporation, and an example here might be a telecom operator, they decide to put a system in a remote site so that they can claim some green credentials. Cost-wise, the area, because it's very far away, probably doesn't generate much revenue for the operator, but they want to do it as a project because besides it looks good, it's a way for them to experiment with this new technology. The other projects that we get asked to do are projects which are sort of enforced by regulatory demand. So there are a lot of vertical markets like mining companies, particularly marine companies, that are looking for ways to reduce the emissions that are much more aggressively controlled by the authorities in their particular industries. And in that particular case, yes, the solution will probably be more expensive than what they are currently using, but the reality is they have little choice. They have to reduce emissions for regulatory purposes. And then finally, we have projects that actually do work in that they deliver a higher value of service in terms of reliability, in terms of overall cost factor. Yes, the capital cost to acquire this technology will be high, but the operating costs will be exceptionally low because I've got no moving parts. I've got very little requirements for big part substitution. So overall, my total cost of ownership between my CapEx and my OpEx should fall in favor of a greener type technology. And we have various ways of helping users measure this. If I take the example of alternatives to, say, batteries plus diesel generators to provide power, either prime power for a village or a community or as a backup type solution, we do look at the existing capital and OpEx costs for the older technology. And from an OpEx point of view, there's a lot of costs there that people don't actually realize that's part of the of their normal daily operation. And when we compare that to the CapEx and OpEx of this greener hydrogen-based technology, and it's relatively straightforward. The operating costs are very low. It's basically an annual maintenance visit, and pretty much it's all been driven by remote maintenance. The system is designed itself to be remotely maintained. So in terms of the big sort of, I guess, the sweet spot that we address is really the limitation that batteries have for addressing things like seasonal variation with renewable energy, particularly solar. So when you're designing a solar plant, typically you're designing it for the worst day of the year. So during the best seasons of the year, you're usually producing more energy than you can store in batteries. Now, by converting that energy to hydrogen, we're actually harvesting that, and we're making use of that to complement the power requirements during the worst season of the year. So the end result is that you may end up reducing your bridging batteries or your batteries to be something considerably smaller, removing the need to have a diesel generator and refueling and maintenance, and even possibly also not having to have as large a solar plant as you would have expected. So in the example I'm going to briefly discuss here is Koi G, which is a small off-grid island in Thailand. It's probably the longest running off-grid site in Asia. Basically they have lots of solar PV, but at night time, certainly in the evening when the load is low, that energy has got nowhere to go. So at night time they start consuming the energy, which is depleting the batteries, and in the morning the diesel generator has to come on to supplement the batteries. And all we're basically doing is we're taking that energy that has nowhere to go, we're using it to create hydrogen, and in turn, instead of turning on the battery in the morning, the fuel cell comes on, and that basically takes over until solar PV kicks in later. So the general sort of approach we have is we size the solar PV in energy for a normal 24-hour day, not historically a 2 or 3 day situation, which is what is normally done. Our system is controlled by software, so it learns how people use the system, learns how consumers use the load, and it basically manages the when and where to make a hydrogen at the most appropriate way. Okay, so in terms of the process, it's relatively straightforward. I need power, I need water. Water can come from a well, can come from a river, can be rainwater collected. We like to run that water through a filter, particularly if it comes from a well. We're very, very water tolerant, but it's more to extend the life of the electrolyzer. When the appropriate conditions apply, we convert that water into hydrogen. We run it through a dryer to make sure it's, there's no remaining water with that hydrogen we produce, and we put that into a vessel. And as an example, a 1 cubic meter vessel, which is about the size of our cabinet, can hold 50 kilowatt hours. These vessels can be sourced locally, and an empty vessel is obviously going to be much cheaper than buying batteries to do the same. To convert that hydrogen back into electricity, I need to run it through a fuel cell, and we can use batteries, but we prefer to use supercaps because they're more green in the long run, and that then provides a load to meet the requirements of the village. So as an example, this is a typical system we've deployed in Malaysia and in Papua New Guinea. It's 40 kilowatt hours a day, can handle a peak load of 20 kilowatts. But what's important, I think, is that the cost per kilowatt is pretty much fixed at 16 cents over 15 years. And that was about, I think using a diesel generator, their cost was around 45 cents per kilowatt hour. The payback in terms of the total cost of ownership versus diesel generator was in about 1.5 to 2 years. Taking that a step further in terms of larger scale systems, and I just need to turn my camera off here at the moment if I can. We have an example here for a mining company in Papua. Their only option was to use 200 kVA diesel generators, and we ran the numbers for them indicating the cost of using diesel generators versus solar plus battery only, plus using solar plus hydrogen storage. And basically if you look here in terms of the solar required for battery only, it was 1.7 megawatt. We're down to about 900 kilowatt by comparison. 1,700 kilowatt hours of batteries. We're using only 300 kilowatt for a bridging battery. And that 1,700 kilowatt of battery would only have given them about 4 hours autonomy at the end of the day, where we were offering days. But the main sort of aspect was the cost saving over the fuel that they would have to send to this remote place would have meant that this 2 megawatt per day solution would have paid for itself in about 6 years. So I'm a bit conscious of time, but I want to just make a good example of what we would regard as a very good potential project, of which we are very sure there are many, many similar examples in Thailand. So the example I'm going to give you is an island called Mafango Island. It's in Kenya. It's based in Lake Victoria. This island is a home to 10,000 souls, 10,000 people. And servicing that island, there is a diesel generator, 200 kVA, and it only operates for 12 hours a day. So this is an existing system where the solution is fossil fuel based, but more importantly, we have a cost structure around it. So we have from last year, from 2022, we know the amount of liters that are being consumed every month. We know the kilowatt hours that are being generated monthly. We know the average kilowatt hours per day, what the peak power is, the time the peak power occurs. And more importantly, we know that the price of diesel, that they are paying, which started at about 123 shillings in January, that same diesel was costing them nearly twice as much. So the big problem they have is the fuel price keeps increasing quite dramatically. So they get to a situation where 12 months later, the fuel is nearly twice what they were paying. So what we're doing here is we're taking money that's already flowing towards a carbon type operating cost, and we're switching that to a renewable energy solution. So the cost for our proposal to provide more energy 24 hours a day comes in, I think, around about 2.2 million euro. So basically just taking what they're spending right now on diesel, they would have paid for their system in about 4.5 years. And that same technology will last them for 15 years. So what we are really looking for in Thailand are situations where money is already going the wrong way towards carbon-based solutions, and we're going to twist that money towards going towards funding a more CapEx type approach. These are the type of scenarios I think that will work very well in Thailand. So at the end of the day, I think fuel cells are inevitable. They are an inevitable conclusion. Governments all around the world are already mandating the reduction of diesel, the reduction of carbon-based emissions. So it's inevitable that fuel cells are going to happen. The issue with fuel cells obviously is, where do I get my fuel? If hydrogen can be produced on site where it's needed, that power or electricity to do that comes from renewable sources, then we have a pretty good solution that's very beneficial for Thailand. So potential projects in Thailand or potential opportunities, any existing site that uses a diesel generator that already has OpEx, convert that OpEx to CapEx, and we use that to make the solution pay for itself. So at the end of the day, this is really the big picture. We are surrounded by water. Thailand is surrounded by nice renewable energy in the form of solar, and storage is really at our feet. We believe that we are sitting on the world's biggest battery, and it's powered by nature. So finally, as I said before, apologies I cannot be there. Kun Thorsten will answer any questions you want. Please feel free to reach out to me. I have my line ID there. I use WhatsApp, email, or whatever. I'm contactable pretty much 24 hours a day because I'm traveling all the time. And I look forward to seeing you all in Thailand at the end of July. And thank you very much for your time.